Okay, so let's start it. And first, we were going to solve several problems. Um, left from the last class is that the side of ABC are in the ratio of 2, 3, 4. BD is the angle bisector drawn to the shortest side AC. So AC is the shortest side. Well, let's say that this is AC. And B is longer, so one side is possibly 3 and the other is possibly 4. So basically, but this is by the ratio, so this is 2, this is 3, this is for AB. So basically, AB is a little bit longer than 3, BC is a little bit longer than AB. And BD is angle bisector drawn to the shortest, so basically angle bisector is bisecting angle AB. And it looks like this. So it's saying that AC is in 10. So the length of AC is 10. Then find the length of the longest segment of AC. So AC basically, here's A, B, C, D. D is here. Then we actually have the result. So the angle bisector theorem states that BA over AD is actually equal to BC over CD. And you actually can rearrange it. The way to rearrange it is that, so this is the side over the opposite and equal to side over the opposite. And what we can do is actually, rearrange it. So basically, um, we can say that um, like BA over BC, we can swap those. We can swap the direction of those because this is a ratio. A ratio basically, all we really need to keep the same is the diagonal. The product of the diagonal is the same. So this is so we can change the position of diagonal to rewrite this ratio into BA over BC. So the ratio of the side equal to ratio of the opposite. So basically AD over DC. And this BA over BC, we know it's 3 over 4. So basically, this, let me say that. So basically, what we are doing is that the ratio problem is actually easier to solve by assuming the a scaling factor. So basically, AD, we can assume AD, a scaling factor if we assume is X, then basically AD could be 3X expressed by 3X, and DC is equal to 4X. So basically 3X plus 4X will be equal to 10. And so 7X equals 10 and X equal to 10 over 7. 10 over 7 is the scaling factor, and the longer side obviously is DC. DC because it's 4X. So if we multiply 4, then it's actually 40 over 7. So 40 over 7 is the answer for this question. So it's a ratio problem. So if you see any angle like, bisector related thing, a lot of time it's actually, will translate into the ratio of the side and you're able to calculate it. So let's go to the next one. Okay. And so the triangle PYT is a, so triangle PYT is a right triangle which py equals 66 and yt equals 77. So basically, you know, it look like this. And so maybe look like pyt. And this is 66, is 77, and this is longest, PT is longest. PT is more than 50, so basically we know that in this configuration, you know, PT definitely is longer than 50, but is that possible that, you know, YT is the longest and that's 77 and like, you know, let's say that PT is equal to 66 and YT is another. So is that possible? I don't know. So basically we have to consider both case. So let's trying to solve this case and check this case. If this is the case, we actually can write, you know, the siding to a scaling factor 6 multiply 11 and 7 multiply 11. So basically we actually just deal with 6 and 7. If we deal with just 6 and 7, then basically the longer side is actually 11, the scaling factor. And then this is 6 square plus 7 square root. That's going to be 36 plus 49 square root equals 85 square root. So basically 85 square root. So basically this actually works. If this works, so if you, and obviously you cannot factor out another square root portion. Oh. So I think the ring is on the wrong channel. Let me try to copy the right information to her. And so basically, if you add those up, it's going to be 96. We also need to check this case. Still, we're going to use this 7 multiply 11 and 6 multiply 11. So this side is actually 7 square minus 6 square root. That's going to be like 49 minus 36 equal to 13. So that's actually 13 square root. So this side is 13 square root multiply 11, and we are not sure if how it compared to 50. And so basically, you know, obviously 13 square root is less than 16 square root, which is equal to 4. So basically it will be less than 44, and less than 44 also less than 50. So basically, you know, this case actually will not work. So we can exclude it. And so let's go to the next problem. And so the first two is a very good example on the angle bisector. One is on the angle bisector, the other is just Pythagorean theorem. And this one, you just have to use the radical format. And if you know how to factor it, it's actually easier to manage with smaller number. And then this one is actually, you know, a problem which related to like PowerPoint. Let's do that. So, and a point P is outside a circle and is 13 inches from the center. So you can draw a circle, that's O, and that's actually, P, and say P is 13 inch. So this is PO is 13, and a secant from P cut circle at PQ so that the external segment of secant PQ is, so basically, we have another line is PQ and QR. So PQR, PQ is, so PQ is 9 inches and QR is inside it is 7. So find the radius of this. So this actually combines a bunch of information. So if I draw so this is a secant. So by power of the point, we can use the secant. If you know the two segment of the secant, you are able to calculate the tangent. Because if you draw a tangent here, so the power of the tangent means that this is, let's say there's a PT, and the PT square is actually equal to PQ multiply PR. So this is just the result from the power of the point. And and PQ basically is equal to 9, and the PR is actually equal to 9 plus 7, and that's equal to 9 multiply 16. So basically PT square is equal to square root of 9 multiply 16 equals to, so this square root is 3, this square root is 4, so 3 multiply 4 equals 12. So this side is the 13 and the tangent equals 12. So the radius is just 5 by Pythagorean theorem. And so this just, use the power point. Let's try to check this problem. The point ABC are on circle O. So basically we draw a circle, center at O. Let's say this is A, this is B, and this is, let's say that C, and so the tangent at A, so basically, if we draw this is that this is a secant, and the tangent maybe look like this. So basically, this is P. The tangent at A and the secant BC intersect at P, and P is lying B is lying between CM, so B is between P and C. If BC equals 20, so this is 20, and PA equals 10 square root of 3, find PB. So PB, let's say X. So basically, this is still PowerPoint. So basically, PowerPoint states that, PB multiply PC basically will be equal to PA square. And so PowerPoint is just, if you draw a point outside, so all the secants, their product, like the outside portion of the product multiply the whole length, the outside portion of product multiply the whole length is actually equal to the square of the tangent. And so basically the outside and the inside is also has another result. Basically, if this is, the cross point X, so XA multiply XB equal to XC multiply XD. So basically, it's a very powerful like theorem, and going to use repeatedly. So you have to be, if you got circle, you got to be paying attention to those. So basically that's PB, if say X, then PC is just X plus 20, because this is segment, at 20 equals PA square. PA is a given value, so that's going to be 10 multiply, if you square, it's going to be 10 square multiply square root of 3 square is just 3. So basically, this is a quadratic equation. So x squared plus 20x, and this is minus 300 equal to 0. And we can factor this easily. X plus 30 multiply x minus 10 equal to 0. And we can double check. Looks like it actually matches. So this solution is trivial, because obviously you cannot have a negative 30 length line segment. It has to be 10. So if we fill in here, this is 10. This segment is 10. This segment is 30. That's going to be 300. So 300 is indeed the square of this tangent line. So this problem is solved. Okay, so we kind of will continue on the like geometry. Today we're going to go through a whole lot of things. I'm not expecting you to understand all. We will trying to open up views. So we're going to go through so what we are going to go through, we're going to go through this is the picture I missed from last time. I put it back, and so we're going to go through the trigonometry, and we're going to go through the like Pythagorean theorem and Pythagorean triple. Pythagorean triple, we're going to go through the trick on how to generate all the Pythagorean triple like under 100. So basically, it's a fun exercise. Then we're going to go through the spatial like spatial angles like ratio and their like trigonometry value, and then we'll go through a few problems, and then we're going to go through the 3D geometry, and then 3D geometry. We're going to talk about Euler formula, and we're going to talk about how to calculate volume and surface area, and then we're going to talk about like analytical geometry, the basics of it. Then if we have time, we're going to go on more on the more of the trigonometry, and so more expanded trigonometry. For the trigonometry we are talk about is only like sharp angle trigonometry. We're going to expand it, to the larger scale, and then use the trigonometry to define the like like trigonometry. What's the indeed use of it is actually triangulation. You are able to calculate like, until right now, the geometry we are learning is that we only is able to calculate length and height and a given right triangle. But trigonometry is actually given any angle, given any side, you are able to calculate anything. This is how the GPS and everything works, and how you measure things. You are not just looking for a triangle or right triangle. Any angle works basically, and you're able to calculate area and the side, and there also a very fun very fun quadrilateral theorem called Ptolemy's theorem, and Ptolemy basically, he was a Greek 2,000 years ago, people already know fun fact on the, like, this is cyclic quadrilateral. So, we will go as far as we can. I don't think I can finish that much, but we will try. And so let's begin. And it's just, the mass is actually just give you the scale of how vast the mass is. And especially if you are going for competition, I trying to like open up a door, show you the way. Obviously, just attend this class is not enough. You have to like, the best way to learn math is that always, open up your view, not just limit your view on the school work, and know the depths and the width of the math, and just, give yourself at least 1 hour each day to read and think and practice. And just because myself is actually, like a math major, and also in the high school, I'm able to like win competition at, like, Shanghai city level, also getting to the like third level. Yeah, Shanghai level, I'm able to get um, like mass competitions. They have like first year level like prize. Then and on the national level, I'm able to get like third level like uh, prize. So it's not bad, but it's also not super good. But anyway, like mass competition is a multi-year effort, and if you know my story, just in the middle school, I have a miserable like mass competition experience. I got like 20 point out of like 100 points. Then on the Shanghai level, on the they have like the qualification tests than the major tests. On the qualification test, I'm able to get 100 points. Basically, I get every point. And on the second round, I'm able to get like first level like price. So basically, that's the level. But it's actually through multi-year dedication. So you do have to learn more extra and practice more. But in the long term, it's just going to help you out a lot. Math, one thing about math is that it's not like don't treat math as something like hobby, and treat it as a business. And like it's not like singing. Singing is or like a lot of artistry work, and those work actually is very, very competitive. For example, if you think you can sing very well, basically when you go to like talent show, most of the case the people will tell you that, sorry, you are not good enough to even reach the entrance level of the business. But math as a business, it's very wide, it's very deep. So most of people love math ended up not really doing the math job, just like I do. I love math for my whole life, but I end up doing the computer job because actually computer earns more and is easier. And so basically, it will be able to land you a good job in the like science area. So basically, it's just open up your door. And if you're really good at math, really love math, you can actually also find so many different layer of the job in the math field. So basically, it's a it's a tool. Basically, everything surround about it. If you dig deep into it, it actually will build your long-term asset very quickly. So, and also math never expire. Math basically, when you're good at math, it's just whole life. And math never, the math, like this cyclic. So Ptolemy theorem, can you imagine this is a like theorem that people mathematician 2000 years ago already discovered, and it bear his name. So if you are lucky one is able to discover some math things, you can put your name on it, and that theorem will live with you forever. Obviously, I don't reach that level, and I just understand things. But anyway, math provide, great potential for a lot of things. So that's kind of what I'm trying to send a message. And be a math lover, and it will reward you handsomely. And so let's begin on today's topic. And um, so last time we actually got a trigonometry. So you are able to, this is a quarter of the unit circle. So this is 1. And given, so basically given the radius of 1, if you have a theta, for example, this theta is 0.7 radian, and you have sine theta plus cosine. Sine theta is just the opposite, and the cosine is the adjacent. Those actually form a right triangle. And so basically cosine theta square plus sine theta square is actually equal to 1. Then basically, this is the tangent. This is the blue one. Blue one still a triangle, which actually with the, so initially the red one has the like hypotenuse is equal to 1. And the blue one is actually the adjacent equal to 1. And the green one basically have the opposite equal to 1. So basically with those three triangles, those three similar triangles, you actually can get 3 identity of the like trigonometry definition. So basically this is 1 square plus tangent theta square equal to secant theta square. So that's for the blue one. Then for the green one, you actually 1 square. 1 square is just 1, so I can ignore the 1 plus this is cotangent theta square equal to cosecant theta square. So that's the trigonometry. And that's from last time. And I think I'll ignore these samples. We will go to the next one. So basically, so these are the Pythagorean proof. I think this is a square used to prove, and pretty much everyone knows it. Basically, the side of the big triangle is a plus b. So a plus b square is actually a square plus b square plus 2ab. And then basically, and so if you just look, this is just from the bigger side. Then from the inside, you can see that actually a plus b square is also equal to c square, and plus 2ab, because it's actually made up of 4 little triangle. So looking from different angle, you actually got those cancel out. You prove a square plus b square equals to c square. And so it's fairly easy to prove. And also given the proof, we actually, this is also like, people in 2000 years ago, how much they understand the Pythagorean theorem. It's also amazing. Is that like, actually not just 2000 years ago, it's almost like 4000 years ago. 4000 years ago, actually in the area of Babylonia, basically currently Iraq, people dug out a clay plate. On it, it actually written down like a dozen of Pythagorean triples. Pythagorean triple are those, numbers that like 3, 4, 5, 5, 12, 13, and like uh, these are scaling up. And on the clay plates, those are not just scaling up, those are unique one. Like, we know that, 3, 4, 5 is 1, 5, 12, 13, and 8, 15, 16, and all those. So basically, people 4,000 years ago already know dozens of like Pythagorean triples. Those are like primary triples. Those are not like scaling up of 6, 8, 9, 15, 20, 25. So how do they find it? And today we're going to go through a very simple exercise of doing this, and then is able to generate those. So the Pythagorean triple actually can be generated by this triangle. So this triangle basically, it's very simple. The principle is very simple. If you put one side as 2ab, and ab could be any integer, and one side is a square minus b square. The hypotenuse is a square plus b square. If you're trying to square those sides, trying to add it up, it actually equalize out. So 2ab square going to be 4a square b square, a square minus b square going to be a fourth minus 2a square b square plus b to the fourth. And this side is a square plus 2a square b square plus b fourth. Those actually equal. And you will notice that because this 4a square b square minus 2a square b square, this expansion on this side and this side is equal. So basically, to find Pythagorean, unique Pythagorean triple, you all really need to do is that, find AB, just pick a number A, pick a number B, it's going to potentially generate those. But there are some, there are some areas that, we actually is able to, so the task is to generate all the Pythagorean triples at less than 100, for example. Let's say that, so there are 16 group of the Pythagorean triples less than 16 of the primary triple, actually called primitive triple. Primitive triple are like triples that those three numbers are co-prime. So basically, how do we find it? So basically, this is our challenge. The challenge actually is not very difficult to be done. So let's just do with this. This is kind of part of the fun. It's, for doing math, part of things to keep your interest in high is actually set up some fun project. So basically, so the Pythagorean triple is actually, one side is 2ab and the other side is a square minus b square. Those are leg 1, leg 2, and then we have hypotenuse is a square plus b square. So basically, if we label it 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is just A. How do we pick A? And this is just how we pick B. And so obviously we cannot pick AB to be the same, because if A equals B, then A square minus B square are going to cancel out. We got 0. That's not, it's a degenerated right triangle, so that's not very good. So we have to be different. So this is, this line get crossed out. We also could make assumptions that, A is going to be less than B, because the symmetry of A and B, we will be able to, without loss of generosity, basically we can assume A is less than B. So we can cross out this part. We're only dealing with this triangle. So this is just a way that I'm going to show you that, studying math and studying things methodologically with some, organized way. So obviously cross out this, 1, 2 is the smallest number I can get. So 1 and 2, let's try. And 1 and 2, basically 2AB. So if we draw this, like, and 2AB is just 4, and A square, like here it actually B square minus A square. So basically, let's say that B square minus A square. And this is B square plus A square. Those are the same because I still can do this. It's actually symmetric. So basically, B square minus A square is just 4 minus 1 equals 3. And add, it's actually 5. So the first one to actually generate 3, 4, 5, we achieve really good success. And the second one, let's see 1, 3. How about 1, 3 works? And 1, 3, we will end up with like, one is that, so 2 multiply 1 multiply 3 actually equal to 6. So here going to be 6. And then this is 1, 3 going to be 3 square minus 1 square going to be 8. And 3 square plus 1 square equals 10. So 6, 8, 10. It actually works, but those are not co-prime because 2AB obviously by nature is going to be even. And if we pick 2 even number, basically, the result going to be even. So those 3 number will be at least having one common factor. So we are not supposed to pick by picking A, B, we should avoid 2 number have the same oddity. Because if they have the same oddity, the second and the third number will leg 2 and the hypotenuse will always be even, and with leg 1 always even because leg 1 has a 2 factor anyway. So everything will have coprime. So we are not going to get a primitive like Pythagorean triple. So we have to avoid. So this we need to avoid it because it's actually, we can cross out those. And we also need to avoid this is both even, this is both odd, then we need to avoid this is both odd, both even, both odd, both even. So basically, we should cross out those selections that will not end with primitive. So basically, by crossing out those impossible cell, we will actually end up with like 1, 2, this is 1, 4, and 1, 6, 1, 8. So then this is, and 2 and 3, and 2 and 5, and 2 and 7, and 2 and 9. And then we have 3, 4, and 3, 6. 3, 6, they actually both are multiple of 6. So 3, 6 will actually produce numbers that, A, B. So the first one, L1 is divisible by 3. and then L2 and L3 going to be also divisible by 3. So it's actually, 3, 6 is also need to be excluded. Then 3, 8. Then this is 4, 4, 5, and 4, 7, and 4, 9. And then this is 5, 6, and 5, 8. And then this is 6 and 7. And 6, 9, we also need to cross it because 6, 9 actually has a common factor of 3. It will generate all the numbers that divisible by 3. So basically, this actually will generate all the numbers that is satisfy our condition. So basically, let's just trying to generate a few. So basically, 1, 4. 1, 4, basically you actually get 2 multiply 1 multiply 4 is actually equal to 8. So let's say 1, 4. And 4 square minus 1 square, and 4 square plus 1 square. So this is actually 15 and 17. So going down this way, it's actually, we actually getting so 1, 6, basically 2 multiply. So this is going to be 12, and this is going to be 35 and 36. So if you, I really suggest you try it yourself. Try to generate, take this challenge, trying to generate all the Pythagorean triples. One thing good about it is actually, if you know how to generate Pythagorean triple, you are familiar with a lot of those. Actually, you will be very fast in terms of doing the Pythagorean problem, because all the tests pretty much they all touch the numbers that like Pythagorean triple under 100. So there are a bunch of those. You will be very familiar with all those 16. And so you pretty much will memorize those, and it's very, even you don't memorize those, it's very fast for you to reverse engineer and generate all of those. And so that's one thing that's fun. And so and then above the like integer number Pythagorean triples, let me copy down those 100, or 16 less than. So if you are able to use that picture, just see how I cross out those impossible ones, and basically you are able to just generate this with the right grid, and it's extremely easy to do, and it's something that you can actually in fact generate all of those based on those grid point, and how you pick AB based on they are not going to generate coprime triples. You will get all those right. And since this is 49, 49, 90 triangle, it's just isosceles right triangle, have 1 square root of 2 relationship. Then this is 30, this angle 30, this is 60, this is 90. Then it actually has, this is A, the opposite is A, this is 2A, this is square root of 3. So this is just half of the, it's actually just half of equilateral triangle. Half of the equilateral triangle, that's this 30, 60, 90 degree. It's used extensively in trigonometry problems, and then you will just use the, the definition of the trigonometry. You should be able to do that, right? And I'm going to just go through quickly, just one of the example. Let me just go through one of the examples. So this is the stack height of those congruent circle of radius 12. So the radius of this is 12 cm. And so when you stack three, it's like a 3-iron pipe of the, equal size. You're trying to figure out the stack height. And then what you notice that this part is one radius, this part is one radius, and this, say, touching each other. So those circles, those three circles actually are tangent to each other. So basically, they tangent to each other. So if you connect their circle center, it actually form a equilateral triangle among their center. So this is also 12. This is also 12, 12, 12, 12, 12. So basically, it is a 24 cm equilateral triangle in the middle. So we can calculate is that draw this, then basically it's equilateral triangle. So this is 1, this is 2, this is square root of 3. So basically, because we actually seeing this is 12 is the scaling factor. So basically this height, the triangle height, the hidden triangle height here is 12 square root of 3. Then add the radius. There are two radius, one radius here, one radius here, plus 24. That's going to be the stack height of those three pipe. And so there are a few other problems, but I think we'll just, you can try to understand yourself based on it. And then these are two very popular, regular hexagon, regular octagon. They actually, you can figure out the area formula for both. This is actually extremely easy. So this is one S. S is the side. So one side of it, this is also S. And so 1/12 of this regular hexagon is S, 1/2 S, and this is square root of 3S. So basically, the height, if you copy the other part on it, you actually can make a rectangle. So rectangle is 1/2 S multiply 1/2 S multiply square root of 3. So basically this is just one triangle out of 6 is this. And the whole hexagon is just multiply 6. You will get the answer. And so 6, you can factor it, 2 multiply 3. So you cancel out one of the 2. So basically, in the end, it's just 3 square root of 3 S square. And divide by 2. There's extra 2 left out. So basically, that's the formula. And this one was also not difficult because I think these two shapes are tested extensively in the tests, in the competition. So I kind of just separate them out. And this, you actually can find out that the area of this regular octagon could be summarized by the middle rectagon. So the rectagon, then you can actually draw it this way. So basically, if you draw it this way, what you will see is that it's actually made up of the inner. This is the inner square with the size is S square. Then you will find that there's an outer triangle corner. There are 4 of those. And 4 of those corner, how big are those corner? It's very easy to find out that if you do a cross line, actually, basically, this is congruent to one of those because the length of the hypotenuse is the same because this is the equilateral, this is also S. So basically, you know, the 4 corner is actually also S square if you find them congruent. So then basically, because this is S, looking at this little triangle, if this is S, and we know it is 1 square root of 2 triangle. So basically 1 over square root of S, or 1 over square root of 2 equals to, so this is just X. What we want to calculate is X over S. And X will equal to S divided by square root of 2. So basically, you know, the height of this portion. So we calculate the middle, we calculate the 4 little corner, then we need to calculate the area of those 4 rectangle on the shoulder. And so that's going to be like the length of those is S, and the width of those is actually S divided by square root of 2. So basically that's just one of those. We need to multiply 4 of those. So basically 4. 4 I write 2 multiply 2 because, and I will 2 multiply square root of 2 multiply square root of 2 again. So basically, you know, use this, I'm able to cancel those. So 2 square root of 2S square is the total area of those 4. So this is 2 square root of S square plus 2S. So 2S is so basically, you know, 2S square is just the middle rectangle plus 4 little triangle on the corner, then plus 4 little rectangle on the shoulder. So that's going to be the whole thing. So those 2 are tested quite often. So basically, just by knowing how to calculate those, and if you forget, you don't have to remember it. Basically, if you know how to use trigonometry, it's very easy to figure out. It's just, you know, it's just based on the ratio of the side of special triangles, you're able to figure out the area very easily. Then, there's this is a fun part of the math, is that sometimes the seemingly impossible area actually is easy to calculate. Is also the result is amazingly simple. And so this part is also like, you know, this is Hippocrates, and he is like 2,500 years ago, they already know how to calculate the area of those double lumps. And a lump is just 2 arcs that formed by 2 different circles, and their intersecting area. It look like a lump basically look like a crescent. So basically, ABC, AXB, and ABC is a semicircle, and AXB is also a semicircle, and BYC is also a semicircle, and AB equals 8, and BC equals 12. Find the combine the area of the shaded lumps. So find the double lump area. So the double lump area is just equal to like the triangle plus 2 half circle minus the white half circle. And basically the half circle here, because AB equals 8, so the radius is actually 4. And so BC equals 12, so radius is 6. So basically the area of this half circle is pi multiplied 4 square equal to 8 pi. And the other one is pi multiplied 6 square equal to 18 pi. So basically 8 pi plus 18 pi plus 48. 48 is just, 8 multiplied 12 divided by 2. And so this area minus is 36 pi. 36 pi is just the, using the Pythagorean theorem, 8, this is the hypotenuse of the right triangle with length 8 and 12. 8 and 12, we don't calculate directly. We will write, 4 multiplied 2 and 3 multiplied 2. No, 4 multiplied 3. So basically, we will factor out 4 and just deal with 2 and 3. So basically, it's 2 square plus 3 square equal to 4 plus 9. And so if I square root of it, it's going to be 13 square root multiply 4. So the radius, or that's actually not radius, the diameter is that. Diameter, so the radius is 2 square root of 13. So if you square it, going to be equal to like 4 multiplied 13, going to be 52. So basically the area of this semicircle is 52, or the full circle is 52 pi, and the half circle is 26 pi. So basically if you minus this, it actually will cancel out all the pi's, will actually go 48. So basically the the double lump is actually, the area of is equal to the area of this right triangle. In fact, it's actually, this guy figures out that, if you make a double lump on those half circle, basically it's going to be equal no matter how you draw it. No matter how you draw it, basically, if I draw it this way, you just have, like half lump differently, but they still have this relationship. So the half, the double half lump will equal to the area of the triangle. So, and then Pythagorean theorem, you also is able to use calculate the height, because if you are, for example, you given a 5, 12, and 13 triangle, basically like 13 multiply A equal to 5 multiply 12. It's just based on area, because the area of triangle could be calculated two way. If you use the two legs, it's actually 12 multiply 5 divided by 2 equal to 13 multiply A divided by 2. So you actually have this relationship. And okay, let's go to 3D geometry. So we just go through the Pythagorean triple, how we generate it, and we kind of use spatial ratio and did some geometry problems. And the 3D geometry is heavily 3D geometry is fairly formula based. So every calculation usually already have a formulas, and for those unconventional one, it's actually usually it's a 2D problem in disguise. You just have to find out the plane which has the right triangle hidden, and use the related information to really solve it. So 3D geometry, we have some terminology. So it's called polyhedrons. Polyhedron is a geometry shape made up of polygon faces, which mean that straight line's edge and assign together at vertex. So those tips are called vertices. And then one two-face join, it's an edge. And then a face obviously is just a flat plane which made up one part of the surface of the polyhedron. And you see altogether like 5 platonic solid regular polyhedron. So these are altogether these are only 5 platonic solids. So tetrahedron, cube, octahedron, and a dodecahedron, and a icosahedron. So this just has 4-face, 6-face, 8-face, 12-face, and 20-face. And so you are able to list the number of the face, number of the vertex, and the number of the edge. They actually follow a formula called, like Euler formula. So basically, the number of the face plus number of the vertices equal to number of the edge plus 2. So basically, you can check them. For example, 8 plus 8 equals 6 plus 2. And it works on all of those. Actually, not just on the regular polyhedron. It works on any polyhedron. So this is just one of the formula we have to know how to use. So this is the Euler formula. You can either write this format or this format. Face plus vertex minus edge equals 2. This is another way to write it. And so one of the things we are quite, popular is called soccer ball. So one popular polyhedron come up very frequently in the contest is a truncated icosahedron. So basically, so a truncated icosahedron is a soccer ball. Basically, it comes out this way. And let's first see the icosahedron. So how do we get the truncated icosahedron? Just the icosahedron actually has 20 face and 12 tip. So at each vertices, we just cut it, truncate it. So basically at each tip we truncate it. We will, by truncating it, because each tip actually has 5 adjacent shape, by truncating it shorter, we actually create a regular pentagon with it. So basically that's why a truncated icosahedron has 20 regular hexagon and 12 regular pentagon. So 12 regular pentagon is created by truncating 12 vertices. And how does all the 20 regular triangle or equilateral triangle disappear and replace with 20 hexagon? Let's try to check. How does that happen? When you truncate it short, imagine you add this line here, also truncate this tip. Imagine add this line here, add this line here. It actually going to create, it will make each triangle face into a hexagon. So basically, a 20 face, so it is each side is icosahedron. So when you truncate the tip, you basically truncate it this way, and the left part will, become a hexagon. So basically, this is just soccer ball. Soccer ball is a fairly popular shape, and it's made up of it's created by stitching together 20 regular hexagon and 12 regular pentagon, and each with a side length of 1 inch. What is the combined edge length of the seams required to stitch together a soccer ball? So this one is actually not very difficult. Basically, because each face, when you deal with 3D problem, and so when you're trying to count the edge, the edge is extremely easy to count because you can do over counting than discount, because each edge definitely is just shared by 2 faces. Edge always shared by 2 faces. And so like other shape, so the edge always shared by 2 faces, no matter how you look. And the vertex could be shared by, vertex need to share by at least 3 faces, but could be shared by up to like, in icosahedron, like 5 faces. And if you have for example, imagine if you have the apex of a um, decagonal pyramid will have 10 faces meet at the apex. So the number of the face going to meet at apex is uncertain. You have to really look at it. For example, this is octahedron. Each tip you have four face meet at each tip. So but the edge, no matter what edge you are looking, it's always 2. So when you deal with like edge counting problem, the easiest way is discount the over count. So basically you have 20 hexagon, so 20 multiply 6. You have 12 pentagon, 12 multiply 5. That's going to be 120, that's going to be 60. So add together, there's going to be 180 edge. And those are over counted edge, because each edge I'm counting here is over counted exactly once more. So basically, if we divide by 2, that's going to be 90. So 90 is very easy to get. Then this shape maybe looks very daunting, and because after you get, a truncated, so this is a soccer ball, then you kind of lose track of how many. So usually edge is easy to count, and when you face a problem, try to counting the tip. Then basically counting the vertex. For example, if we need to know the number of the vertex in this soccer ball, then basically this formula come into play. And we know there are 32 faces because 20 plus 12 is 30, and plus vertex and minus 90 going to be equal to 2. So basically, if you fill in those numbers, you actually got V equals 60. So basically, a soccer ball has 60 vertices, has 90 edges, and 32 faces. So that's the way that you're able to. There's another example of snug cube, but I don't think I will cover it. They have a lot of exercise, very fun in terms of trying to calculate number of the vertex and number of the edges, number of the faces. So you can practice over there. And this is the prism and the cylinder. And prism, are just shapes with two parallel faces on top and bottom, then linking those two faces need to be congruent. And those two congruent faces are linked together by a rectangle or parallelogram. And if it is linked by parallelogram, it's called oblique prism. Oblique prism is just, slanted, it's not straight. And if it's straight and it's a regular one, then it's every side has to be a um, rectangle. And then cylinder. Cylinder is just, bring this regular down to extreme. Basically, you actually got a right cylinder. And the volume of the cylinder is very easy. It's just base multiply height. And you can imagine it by slicing it out horizontally. Then because each slice has the same area, then the volume must be like, the section area multiply height. So that actually makes perfect sense. And then there's a surface area. Surface area is just lateral surface. Lateral surface is the surface area, not including, the top and bottom. And then for a cylinder, basically the lateral surface actually 2 pi r multiply h. So if you imagine you cut aside this side of the cylinder and roll it out, so then it's a rectangle. The length of the rectangle is 2 pi r. R is the base radius, and then the height of this rectangle is h. Then plus top and bottom. Top and bottom each are circle is just pi r squared, because two of those is a 2 pi r. So it's very easy to imagine this formula. And the pyramid and the cones are just a little bit different. And then the lateral surface actually is the summation of all the triangles. And the triangle, for example, the triangle on a regular pyramid, the height of the height on this side called slant height. Then it's just the side length multiply half of the slant height. Then it's the area of one of the slant triangle. Then multiply by the n, you will get how the total area of this regular prism. Then add this area of the regular gun, you will get the whole surface area. Then bring it to extreme, it's actually the cone. Cone basically, the surface area, the lateral surface area is actually, pi r multiply s. S is the slant height. So this is actually fairly easy to imagine, because we are just calculating the sector area of the circle with the radius, the slant height. So the full area is 2 pi s. 2 pi s square. But the full circle is 2 pi s. The sector length is 2 pi r. R is the base radius of that circle. So basically, I'm just doing a proportion of the area of the sector is just proportion of the big circle. So I'm using the ratio So the ratio between the sector and the big circle is R over S, because it's just, the arc length over the full circle length. So basically, that's the ratio, multiply the area of the full circle with the slant height. You actually got the lateral surface of pi r s. And adding the bottom surface area, you will get a full area of the this cone. And with both cone and prism, their volume is 1/3 of the base area multiplied the height. And you can watch YouTube on how this formula works. Basically, people can cut out cone and other shapes, just trying to fill up trying to put in water, try to fill up the, a cylinder of the same height. Basically, it takes 3 cones to fill up the height. So that's why it's 1/3. And then we have the sphere formula. Sphere formula, the area is the surface area is extremely easy to remember. It's just area equal to 4 pi r, because the big circle on these is pi r square, and it's just take 4 big circle to cover the full surface area of a sphere. Then the volume is actually, you actually can read it this way, is pi r, 4 pi r cube divided by 3. It actually has there are YouTube on how surface area and the volume are related. It actually has everything to do with the volume of the pyramid and the cone. That's why 1/3 has a place to play here. So basically 4 pi r related to cone of 1/3, you actually get this volume. So it's very easy to remember. And let me just do a single problem, just show how the 3D geometry basically is 2D geometry in disguise. For example, this is a cube inscribed within a hemisphere. Hemisphere is just half of the sphere, and the cube has a 2-inch edge. What is the surface area of the hemisphere? So what we can do is that we can, the trick to do this problem is that draw this problem in different projection. So basically, if I do light projection from top to bottom, I will find the shape like this. And so this is the perimeter of this half sphere. And then this is 2-inch edge. And then basically this is in the middle. This is right in the dead center of the big circle of the sphere. And this is, I can cut into 1. So this is 1, this is 1. Then this is square root of 2. So this is the way. Then basically, I'm going to connect the diagonal of this and imagine I project the light in this direction perpendicular to this diagonal. So basically I project this in the direction of this, and basically this tip touches this big circle going this direction. So if I project the light this way, I actually will find a semicircle going this way, and this is actually a square that looks this way, And with this height, the height going to be the same as the height of this cube, going to be 2. But the length of this is not, because this is actually, because you project perpendicular to this, you actually will get square root of 2 here and square root of 2 here. So basically, you know, this is 2 square root of 2. So basically, but we need to find the radius of this semicircle. So basically, this is a right triangle we're going to deal with. One side is 2, the other side of square root of 2. We're going to calculate the hypotenuse of this triangle that will be corresponding to this semi-sphere's radius. So that's going to be 2 square plus square root of 2 square, and the square root equals to square root of 4 plus 2 equals to square root of 6. So basically, so do you see that, you know, the problem, 3D problem usually are 2D problem in disguise. You just have to find out the right way to create a 2D projection. How do you cut a 2D projection? Basically, shine the light from different angle, which makes sense. Why don't I shine the light front back? If I shine the light front back, basically it's going to look like this. I'm going to end up with a shape that don't touch. You know, this is 2 by 2, 2 by 2, but it's not going to touch the edge of the semicircle. So that do not give me any insight. It's useless. So I have to find out the right angle to view the problem in the right way. Then I actually got a surface area. So the surface area of the hemisphere, basically the surface area is at the top surface and the bottom surface. The bottom surface is just pi r square, and the top surface basically is 2 pi r square, because the full sphere is 4 pi r square. So hemisphere, like curved. So basically added together, it's actually going to be 3 pi r square, and the r is square root of 6. And square root of 6 square is going to be 6. So 3 multiply pi multiply 6 equal to 18 pi. So 18 pi is the surface area of this hemisphere. So 3D problems are not difficult. See, either just you have to, you know, plug in the right formula, and there are a bunch of for you to remember. And then also, you know, 2D in disguise or combination of those, you just have to like project the light in the right angle and create a 2D image, and then use Pythagorean theorem to get it. And then 3D shape also have like edge count and vertex count usually can be done using the Euler formula. Then we actually have the scaling factor for the area. So just remember the scaling, if it is a 2D shape, if you scale up, you know, if you double the edge length, you actually end up the 4 times the area. So basically this is one area, because if you double it on both sides, it's actually 2 multiplied 2 equal to 4. Then similarity and the volume, basically, you know, if you volume is just adding one more dimension, it's actually going to be 8. And then yeah, I think we still have a bunch of content to cover, but I'm going to go through a little bit fast because those are much more for the like knowledge of the like previewing. I don't think it's going to be really good for the contest unless you are very dedicated to run those. It's kind of affiliate because one thing about AMC10 preparation of AMC10, I'm also attaching together a lot of AMC12 problem because it's very hard to make, dissect those two, and because those are just very much linked, and there are a lot of problem between AMC10 and AMC12 are shared, and if you are on AMC8, pretty much it's amateur thing. Pretty much every student will go with it. But if you go on AMC10, usually you are looking for to be at least amateur level for the math. And a lot of people, a lot of students actually are serious contender for future math or science major. So basically, I think you guys are the later category. So you are really, serious contender for math and science major, and other general engineering major, you basically all need to be good at math. So basically, I'm going to go through those. And so you are exposed to more advanced topic, and then know which direction you're looking for and where to spend your time. So this is the labeling the plane. And so labeling the plane is actually a major advance in geometry. Basically, it's actually create a, because geometry, it's a fairly matured, it's actually most matured math branch for almost 2000 years ago, but on the other side, on the flip side, it means that for 2000 years, actually, the field of math or the geometry has no advance. It's a stagnant area until, the algebra come into place. Then also like the people link algebra together with geometry to create analytical geometry, which, create like Cartesian or polar coordinate system. Use the coordinate system to link arbitrary location in the plane or in the space with any number, and also place them together with algebra. Then you are able to deal with any position and any location, and the usefulness of this field became astronomically higher and much more practical. Right now, basically, we are living in a 3D space with like, GPS ubiquitously everywhere, and you are able to travel with it. And there are so many applications that, it's all based on coordinate system. So how does it work? We all know the number lines, and if we cross two number line, you actually could go a coordinate system, and you have ordered pair is able to fully represent the whole plane, just like a single number is able to fully represent the whole real number. And you also, so basically, because here's a famous mathematician called Descartes, develops this system. He may not be the earliest one. There's a debate on whether or not he was the earliest one to use it, but obviously he was the earliest one to advocate it. And so basically, people link this system with his name, Cartesian. And um, Descartes is a French, I think one of he's like, religious name has Cartesian in it, so it's became this name for the coordinate system. And the same, just keep in mind, it's not the only system. There are other systems that polar or coordinate is actually use another different pair. And for example, this is a system which use radius. It's a radius angle pair. For example, this is 3, 0 because the radius is 3 and the angle is 0. And here is like, here, for example, is radius 2 and angle 60, or you can say angle like 2 pi divided by 6 or pi divided by 3. So basically, you are able to, for example, this place is 1 and 240 degree. Or you can say 1, 2 pi divided by 3. So basically, actually it actually is 4 pi divided by 3. So basically, this is the 2 ways of doing the coordinate system. And so which one is good for which? So basically, if you are dealing with a lot of horizontal and vertical movement, then the Cartesian plane is the one much easier to use. But if you are dealing with rotation action, actually the polar system is easier to use. And then what are they good at? So basically, when you began to use the coordinate system, then you actually is able to represent the lines on the system with a linear equation. For example, y equals mx plus b. M is the slope and the b is the y-intercept. And then you are able to do the parallel line just with the same slope and the vertical line with slopes that multiply to -1. And then under the coordinate system, you're able to easily calculate the distance with the Pythagorean theorem. And because you are able to create a right triangle with the difference of the x and y coordinate, then the hypotenuse is going to be the distance, and you can use Pythagorean theorem to calculate the distance. And with the distance, you are able to like create a circle, basically. X squared plus y squared plus ax plus bx plus c. Basically, this is actually more generic form for the circle. You are able to complete a square and is able to convert this into a circle formula. And then coordinate system using the analytical geometry is much easy to calculate certain actions. For example, the intersection of 2 lines, it's just solving the equation systems which represent 2 lines. And also it's very easy to calculate the middle point or proportional point. Those are the easy part of it. And then we are going to talk about trigonometry function. And trigonometry function, last time what we did is that using this shape to represent trigonometry function with a angle less than, so this is theta is less than 90 degree and greater than 0. But what we can do is actually expand this definition to any angle and also to angles bigger than 360 degree. Actually, there's a great animation on the Wikipedia. Just do the yeah. So basically, you are able to plot this number with sine and cosine. Yeah, let me freeze it. So if I freeze this, freeze at here, let me copy it here. So this is an angle bigger than 90 degree. So here, the sine function is just the y coordinate divided by 1. So it's still a bigger 1. And then this basically is the x coordinate. It's actually a negative number. So this is the 0 line. So basically, in other location, it's just became in this area, it's going to be a negative. So basically, you can actually spin this around and around, and the theta could go to infinity. It's just going to repeat the pattern. It's actually has a period for repetition. The repetition period is 2 pi for both sine and cosine. And for tangent and cotangent, it's actually, the period is pi. So basically, we are able to expand the definition of sine cosine above the 90 degree and create a period function on those. So this one is the cosine. Cosine at 0, it's going to be 1. So that's cosine, and this is the sine. And the cosine and the sine, those are exactly the same shape, but it's just shift. So sine just cosine shift right to pi over 2. And the tangent is going to be, it's the period of each tangent is actually pi. So this is negative pi over 2. This is pi over 2. So basically, with every half circle, not full circle, the tangent function going to repeat itself. And then the sine and cosine pretty much could represent all the periodic function. So basically, if some function oscillates very high, it's the amplitude. Amplitude just represents how high it's oscillate. Then also there's a frequency. Frequency is the period. For example, if I transform this function with f2x, then basically, it do not with the 2 as a factor, it do not need 2 pi. It only, because it already have 2, I only need 2 pi. So it will shorten the period of the oscillation by half. And then pi, sine and cosine, they actually has a phase shift. So basically they shift the phase by 90 degree. So, and then what's the use of this? What's the use of the trigonometry function by doing so much of those? It's actually, trigonometry function is very useful in terms of studying vibration and season and the repetition and everything with period. For example, in the 1700s, Daniel Bernoulli, and he finds that guitar string, make the sound, and it's actually, can be represented by the sine functions. And obviously, when you pluck the string, it will come up with different sound. It's just combination of sine function with different period. And it's just overlay of it. And then Fourier, the French engineer Joseph Fourier established this formula that all the periodical function could be represented by like series of sine and cosine function with different frequency. So basically, that's a phenomenon. That's a phenomenon effort. Basically, it actually paved the fundamental and the theoretical foundation for a lot of the sound engineering. Sound engineering, basically, it can mimic with very limited electronic device like speaker, you are able to reproduce the sound of animal and instrument and anything, basically. It's just internally, it's just simulate the sine wave, which made up of those sound, and it dissect it and then use electronic signal to save it and then transfer it, then reproduce it. The component, so any sound is made up of component of different sine wave. So if it can reproduce those sine wave, it can compose and up those information. So that's a quite phenomenon thing. So it just show how far the math can go, and with a lot of discovery by this. And so it's just all those, it's just like expand the trigonometry function above the 90-degree range and find repetitions and expand it with different frequency and the amplitude and the phases. You are able to achieve like unimaginable things that really happened. Then this is just the periodical behavior of trigonometry function. Then we also has another group of the function called, we have sine function, and we also have arcsine function. We all have cosine function. We have also arc cosine function. Arc function, what is arc function? Possibly will ask. Arc function is just ask the question a different angle. And sine function is that given an angle, I'm trying to find the ratio of the side between different side. So that's all about the fundamental meaning of the sine function and our trigonometry functions. And arc function on the trigonometry function is that, you know, given the ratio of the side, what's the angle that creating this ratio? That's the question it's asking. So it's actually going backward. It's actually a, it's actually is the inverse function of the trigonometry. For example, you know, if we are 1,000 feet away from a 500 tall tower, and we wish to aim our laser at a mirror mounted at top of the tower, at what angle should we shoot our laser? And yeah, this is 1,000 feet away, and this is 500 feet. So the tangent means the opposite over the adjacent is actually 1/2. So basically, theta equals tangent -1. -1 means it's just trying to find the inverse of this ratio. And so it's called arctangent. And the arctangent also could have multiple values because I can aim like this angle, but if I spin myself, like if I do several somersaults, and I still can look at that angle with a different theta. It's just, you know, 360 multiple at the original angle. So basically, you know, arctangent actually has a principal value, the values that within the negative pi to pi over 2, then you can repeat the pattern that find other value still works. And then the trigonometry function, the sine is a odd function and the cosine is an even function. And this is a very useful proof that, you know, to create more of the sine function identity. The sine function identity, I'm not going to prove it because it actually prove it here. It's just take extra time, just trying to show you the new field. It's a more relaxing and just, you know, knowledge thing. So basically you are able to create two triangle with alpha and beta, and with the side relationship, you are able to show that sine A plus B, basically the sine of the combined angle is equal to sine A multiply cosine B plus sine B multiply cosine A. So this is the identity for sum of the angle in the trigonometry. Then they also have the sum of the angle in the cosine. And then they also have the double angle for the sine, cosine, and the tangent. And they also have like half angle. So basically, that create a lot of trigonometry function. And then you will ask, what's the use of the trigonometry function? And, you know, other than reproduce the sound wave, they actually, you know, they open up the door for like a universal geometry. You know, like before this point, the geometry we are talking about is almost always the right angle geometry or like parallel line geometry. So basically we had to find a right angle so that we can use the like the Pythagorean theorem, and we have to find certain, you know, parallel line, we find the same angle. Then right now, given the trigonometry function, we can deal with any angle. So that's the freedom it brings us. So basically, you know, that's why we can only like using 4 satellites in the sky, we can uniquely identify a location in 3D on the Earth. And so that's actually, that's how trigonometry works. And, imagine we always have to use right angle. Then basically, the right angle just a lot of places don't exist. It also happens so infrequently. It's impossible to achieve that type of thing. Or you have to line the whole sky with one one 1 trillion satellites. That's ridiculous. So basically, so the quintessential thing is that, I'm just showing where the document is. You can dig deep into it because actually it takes quite some time to really go through and understand it. But the quintessential meaning is actually quite easy. So basically we have A, B, C to prove this. What we are trying to prove is the law of cosine. So the law of the cosine is basically the expansion of Pythagorean theorem. It expands to any angle. So c squared equals a squared plus b squared minus 2ab multiply cosine c. And so if we given an angle, and the right angle, for example, special angle is right angle, cosine a right angle will be 0. So basically, this actually, Pythagorean theorem is a special case of law of cosine. So the law of cosine is proved by draw a triangle. This triangle actually is the the tip A is at the center of the triangle. Then we use the relationship. So this is actually, we actually create 2 pair of the crossing line. We are using PowerPoint. We are using the PowerPoint formula to really create relationship between them. And we also make assumptions that, AC is actually just equal to 1. So basically, by using those, the length of the line create a product relationship, then we are able to prove that c squared equal to a squared plus b squared minus 2ab cosine c. So this is the cosine, law of cosine. Then we also have law of sine. And the law of the sine is much easier to understand. It's just, given any angle C, A, C, B, basically we can, because it's facing the same arc, AB, we can create a right triangle. And then we can create a right triangle. And this right triangle has to go through the diameter. It's AE is always coincide with diameter. So basically, AE, the sine of AE, sine of AEB is AB over AE. So basically, it's actually the sine C is AB over AE equals C over 2R. 2R, R is just, the circle's radius. So basically, and it actually created a very, so basically it relate the sine with the sine value of all 3 angles of a triangle with the circumradius of this triangle. So that's a phenomenon, theorem. And with both theorem, we actually is able to do triangulation. Triangulation means that you can actually, given any angle, given any side that, if you, for example, 2 sides and 1 angle, or 2 angle and the 1 side, you are able to determine any remaining length of the side and any remaining angle of the triangle. So basically, it has a lot of power in terms of, so that's why human being is able to to really advance the technology. Those are all based on triangulation, a lot of practical use. is in this area. Then, so we actually come up with like, you know, the area we have to already have several formulas. So basically this is A multiply A is the base, the height of A, the height on the A divided by 2. So this is the basic formula. So this is just expansion of the basic formulas. 2A is the same. The height could be represented by the side B multiply sine C. So if we draw the, so if we have the, this is A is BC, and this is A. So basically this is the angle C. So basically, and the height to B, the height over B is basically sine C. So basically, you know, A multiply B multiply sine C, basically this is actually equivalent to this, and is then E is equal to R. R is the in radius of the circle multiply its semi parameter. So this is the normal formula we got. And then this is the famous Heron's formula. Heron actually is also a Greek. It's also fairly, you know, phenomenon because 2000 years ago, trigonometry function is not developed, but without trigonometry function, they actually find out the Heron formula anyway. So that's how phenomenon, you know, the ancient mathematician is, and they are quite good at it. So what we are doing is that, you know, given that formula, and also given the science, so basically here, see, area of the ABC equal to AB divided by 2 multiply sine C. And the sine C was replaced by the, this is the identity. If we replace the sine C by identity, because sine a square, you know, C plus cosine square C equal to 1. So basically replace this by the identity, we actually will get this, the cosine. And the cosine, basically, cosine C going to be replaced by the law of cosine. So let's see the law of the cosine. So the law of the cosine, basically C square equals A square plus B square minus 2AB. So if we solve for C, basically we can just C square minus A square minus B squared divided by negative 2AB is actually equal to cosine C. So cosine C can be expressed by 3 sides. So all we did here, all we did is just use the sine and cosine identity, then also replace the value by cosine, law of cosine. Then we are able to, you know, replace the, you know, figure out those relationship and simplify it to, you know, Heron's theorem. So that's a theorem discovered like 2000 years ago. People already know that. And so the law of the sine, so this one, basically, you know, Heron's theorem is using law of the cosine to calculate it. And so if we have two laws, law of sine, law of cosine. Law of cosine produce Heron's theorem. If we use the law of sine, then basically ABC equals AB multiply sine C. And the sine C by the law of the sine, basically sine C, basically it's a ratio between C side and 2R. 2R is the circumcircle radius. So basically, with the sine law, we replace the sine c with the r and the c. Then we produce ABC. The area of ABC is product of all three sides divided by 4 times the circumradius. So basically, we actually got this formula. This formula gave us one extra way to find the area of the triangle. Also, it gave us the way to find the circumradius if we know the area and all three sides. If we know all three sides and circumradius, we can find the circumcircle. And we have never talked about how to find that before, and this is where you can do it. And then basically there are more important lines that there's a Stewart theorem. A Stewart theorem, basically, we are dealing with Cevian. Cevian means a line that, going to the other side. And we're trying to find the length of the Cevian. And then the Stewart theorem basically is still using the sine cosine function. And it's using actually the cosine ADB, and cosine ADB can be represented by the side of CDM, so CDM. And cosine, actually, a cosine's angle is actually equal to negative of its supplement angle. So basically, with this equal, the same value could be represented by those three sides. So basically, we are able to produce a Stewart. Stewart is a mathematician like living the 1700s. So their theorem was developed much later. And so we actually have this formula. Basically, they actually make it easy to remember by like CMC. Basically, it's C square M of M plus B square M equals DAD, dead plus dead man. So DAD. A is basically BC. So if you read it. And what's the use of it? So with Stewart's theorem, we are able to calculate the length of angle bisector. So the angle bisector D, if you have the length of the angle bisector D square equal to BC multiply 1 minus A squared divided by B plus C square. So, so until here, we actually get the way to, figure out all the three Cevian. So basically, this is the angle bisector. And then we also have a way to figure out the like median, and also have way to figure out the height. So basically, let's go to the last portion of this introduction, is that, Ptolemy's theorem. And then we know that the cyclic quadrilateral, the opposite side is supplementary. So the opposite side, A plus C equals 100 and B plus D is 100. Then it's fairly easy to find out, whether or not the quadrilateral are cyclic. Cyclic means that, all 4 points are located, on the same circle. And you can just judge the opposite, or you can judge the like A and B if they are the same. congruent, it's also cyclic. So, and finally, we come with Ptolemy's theorem. And Ptolemy's theorem basically is that it's stating that on a cyclic quadrilateral, we have this relationship AC. AC basically is the opposite. AC and BD. AC plus the product of AC plus product of BD equals product of EF. EF is just, the diagonal. So the product of the diagonal is equal to a product of the sum of the product of the opposite side. And Ptolemy's theorem, imagine this is also like a 2,000-year theorem. And so like ancient Greek, they already know so much about triangle and how to calculate all those things. And at the time without the help of the trigonometry. So that is actually quite phenomenon. And okay, I think that reached the end of today, and a lot of parties actually introduction on like the trigonometry and its more advanced use, and also extra formula in terms of calculating the more on calculating area and the circumradius. So okay, I think I will assign homework and have a nice one, everyone. And we'll be more focused on the easy part, and this is just introduction. But it's just trying to open your eye for this, and it's more focusing on the 3D and Pythagorean theorems, those easy part for the homework. Yeah. Okay, have a nice one, everyone. Bye-bye.